This lesson is continuity in reactive elements. Our objectives are to introduce the unit step function and to know when the voltage or current cannot change discontinuously. It builds on the integral IV relationships for capacitors and inductors. We begin with the unit step function, also known as the Heaviside function. It's used in describing a source, a voltage source, or a current source. It's defined symbolically, as I'm showing here, a function that takes the value 0 for negative time and 1 for positive time. And here's the plot of it. And notice that it is discontinuous at the origin, and we will not be concerned what is the exact value at the origin, only that it takes the value of 0 for negative time and 1 for positive time. Next, I want to define what I call the running integral. In this function of time, y of t, we see t in two places. It's the argument of y, and then on the right-hand side, it appears only in one place, which is the top of the upper limit of the integral. As t increases, more area is captured by the integral. Let's consider then the integral of the unit step function. Here's the step function, as you saw before, and here is its integral. Notice that the integral is 0 for negative time. That's because no area is captured for negative time. And then for positive time, as t grows, we're going to progressively and proportionally capture more and more area, producing this ramp characteristic with slope 1. Now the integral is continuous at t equals 0. And we say that y of 0 minus is equal to y of 0 plus. Now 0 minus is that time that's infinitesimally less than t equals 0, and 0 plus is infinitesimally greater than t equals 0. We use this notation later when we talk about initial conditions for second order circuits. Now the voltage in a capacitor has this running integral form that we were just talking about. Notice that it's divided by C, and therefore the voltage in a capacitor is going to be a continuous function of time. Let's consider this example that C is 2 farads. The initial voltage is at t equals 0 is minus 2 volts. So that means that for us T naught is going to be 0. And then our current is given as shown. Now the voltage that goes with this is shown here. We start off at minus 2 because that's the given initial condition at the origin. And then we see, because the current is constant from 0 to 2, our voltage has this ramp characteristic. So the only challenge for us is to determine what is the maximum value of the ramp. And we can figure that out because at t equals 2, the integral will have captured all of this area, which is 2 times 4 or 8. But don't forget, you're going to be dividing by C, which is 2. So the voltage over this interval of time has to increment by 4, 8 divided by 2. And that's what it does. It goes from minus 2 to plus 2. And then, since the current is 0 after that point, the integral doesn't capture any more area, and the voltage stays constant. So we notice that this is the voltage is continuous, even though there is a discontinuity in the current, but because it's a capacitor, the voltage is continuous at that point. All right, the same sort of thing holds true for inductors, but for current. So current is continuous in inductors. And I'd like for you to try the following quiz. The mathematics is really the same as we just went through for the capacitor. So let's suppose that we have the initial current at t equals 0 is 1 amp, the inductance is 1/3 henries, and the voltage is as shown. Then I'd like for you to please choose one of these 3 curves for current. in considering the choices here for the current, we can rule out the case in B because of its discontinuity, because we know that the current in an inductor cannot be discontinuous. So that rules that one out. All right, so the other two are continuous, and they both begin at 1, which is what they ought to be starting at because of the initial condition. They both have a downward ramp, which is correct for voltage being negative in that period from 1 to 2. They differ in how much they drop. So let's consider how much the ramp should drop. The area, if you consider what the current would be at time equals 2, it's going to be the value of this area divided by the inductance. Since you're dividing by 1/3, you're actually multiplying by 3. So you take the area, which is -1 times 3, gives you -3. So our ramp should change by a net of -3. This one only changes by -1, so this one cannot be true, and that leaves A as your correct one. In summary, because of the integral in the VI relationship for capacitors and inductors, the following cannot change discontinuously: voltage in a capacitor, current in an inductor. Thank you.